Good day, students. On this clip, we're going to be doing some review problems on derivatives. So it's just a practice set of problems to sharpen your skills on the art of differentiation. Okay. This video assumes that you already have knowledge of the power rule, the product rule, the quotient rule, and the rules for differentiating trigonometric functions. All right. So let's go ahead and take a look at the first example, but let's write down the instructions first. So the task is to find the derivative of the following functions functions. We're gonna do it with respect to t. Okay, with respect respect to t. All right. So what we're looking for, no, with respect to x. Sorry, with respect to x. So what we're looking for is basically dx of the following functions. All right. Okay. So let's start with function number one. What if we had y equals 3x to the fourth minus 1/2 x to the third plus 1/4 x squared. Okay, this is a polynomial function. So what we're going to apply is we're going to apply the power rule, and we're going to differentiate each term by term. All right. So let's go ahead and look for the derivative. I'm going to use prime as my notation of choice here because it's much more convenient to write over and over again. All right. So y prime is going to be, now I'm going to differentiate this one using I'm going to factor out the constant. Anytime you have a constant, you factor it out. So it's basically 3 times x to the fourth prime minus 1/2 times x to the third prime plus 1/4 times x squared prime. Okay? Anytime you have a constant, just factor it out and just focus your energy on the powers, right? So you can apply the power rule to differentiate in the power. All right? So the power rule is basically, if you have x to the n, then the derivative with respect to x of x to the n is simply n times x to the n minus 1, right? So that's the rule I'm going to be applying here. So let's do it. We're going to do it for this term, and that term. So y prime is going to be 3 times whatever the power is comes to the front of the variable, and then you subtract 1 from the power, 4 minus 1. Okay? Minus, bring down this 1/2, times, bring the 3 to the front, 3 times x to the 3 minus 1. Okay, you always subtract 1 from the power as suggested in this formula, right? So it's 1/4 times 2 times x to the 2 minus 1. Just bring the power to the front and then subtract 1 from the power. Alright, so this is going to be y prime, equals 12x to the third minus, we multiply this across 3 over 2x squared plus 2 over 4 is just 1/2, right? Plus 1/2 x. And there goes your final answer. Alright, so just remember, anytime you have a constant in front, just factor it out and focus your attention on the function that has a variable in it. Alright, let's try another example. Example number 2. Still looking for the derivative. In this case, the function under consideration is y equals 7 minus 4x to the third plus 5x to the sixth. Alright, so we're going to be differentiating every single term. So y prime is going to be, now this is a constant right here. So I can factor out anything. I could put an x to the 0 there, but for this one, I'm just going to write 7 prime because I want to show you something concerning differentiating constants. Factor out the 4 times x to the third prime plus factor out the 5 x to the sixth prime. Alright? So what is the derivative going to be? So y prime is going to be What is the derivative of a constant? Since it doesn't change with respect to x, the derivative of a constant is going to be 0. All right? Minus 4 times, we're going to apply the power rule here again. The 3 comes to the front, times x to the power, you subtract 1 from it. 3 minus 1, plus 5 times the power comes to the front again. 6 times x to the, and then you subtract 1 from the power, 6 minus 1. Okay? So let's simplify this further. We have y prime equals 4 times 3 is 12, negative 12x to the second, 3 minus 1, plus 5 times 6 is 30, x to the fifth. All right? So there you go. Oh, yeah, we can even write this in standard form. Let's write this nice and neat. So we can rewrite this as y prime equals, since this has a bigger power, 30x to the fifth minus 12x squared. Okay? That's just cosmetics. We're just dressing up our result. All right, let's move on to question number 3. Question 3, we have y equals 3x plus 2 divided by 3x minus 2. All right? All right, so in this example, we're going to be using the quotient rule to compute the derivative of this function. So what is the quotient rule again? So let's say we have two functions, a quotient of two functions, u over v. If we take the derivative of u over v, is basically v, the denominator, times the derivative of the numerator, minus the numerator times the derivative of the denominator, over v squared, right? And a mnemonic device that some people use, they just call the top high and call the bottom low. And then they say the derivative high over low prime is basically low times the derivative of, they say low d high minus high d low over low square. Okay? So I don't know how this helps people, but some people use this whole idea of low d high minus high d low over low square to remember the quotient rule. But I just use v u prime minus uv prime over v square. All right, whichever one makes you happy. All right, so in this problem, this is going to be my u, and this is going to be my v. All right, so I'm going to use this formula to compute the derivative here. So y prime is going to be v, which is 3x minus 2, times u prime, which is 3x plus 2 prime, minus u, which is the numerator, 3x plus 2, times the v prime, which is 3x minus 2 prime. And then we're going to divide that whole thing by v squared, which is 3x minus 2 squared. Okay? So divided by 3x minus 2 squared. Okay, so let's do this. So y prime is going to be 3x minus 2 times, we're going to apply the power rule here. If we do term by term differentiation, the derivative of 3x is just 3. And then the derivative of 2 is 0. So this one is just going to be 3, okay? And then minus 3x plus 2. And then using the power rule here again, the derivative of 3x is just 3. And then the derivative of 2 is 0. Alright? And then divide that whole thing by 3x minus 2 quantity squared. Alright? If we simplify further, we're going to have 9x minus 6 minus, and then distribute the 2, minus 9x minus 6 divided by 3x minus 2 squared. Okay? Divide that whole thing by 3x minus 2 squared. Alright, and then we'll just simplify the numerator in just one last step, and that will be that. So that the final answer is going to be, these are opposites, so they cancel out. You're going to have negative 12 divided by 3x, the quantity 3x minus 2 squared. So there goes your final answer. All right. Okay. Now let's move on to question number 3. Question 4. This is 3 we just did. Question 4. The function under consideration is going to be y equals 5 cosine x, 5 cosine x sine x. Alright? So in this case, we have the product of two functions, namely trigonometric functions. So we're going to be using the product rule. So if you have u v prime, the product, using the product rule, is going to be u v prime plus v u prime. Alright? So there goes the product rule right there. Alright, so let's apply that to this. In this case, this is a constant, so we can factor it out. So y prime is going to be 5 times cosine x sine x prime. Alright, so this is going to be this piece right here, the cosine function, is going to be my u, and the sine function is going to be my v. This 5 hasn't factored out, so we're not going to look at it. Alright, we're just going to multiply 5 by whatever result we get. Alright, so let's go ahead and apply the product rule to this scenario. So y prime is going to be 5 times u is just cosine x, times v prime. V prime is going to be sine x prime, plus square bracket here, times v, which is sine x, times the derivative of cosine, which is cosine x prime. Alright? Now, remember your trigonometric rules for differentiation. Derivative of sine is cosine, and derivative of cosine is negative sine. So y prime is going to give us 5 times cosine x. Derivative of sine is cosine, times cosine x, plus sine x. The derivative of cosine is negative sine x. Alright? Now, if we'll simplify further, we're going to have y prime equals 5 cosine square x minus sine square x. Now, if you think back to trig, remember this is the double angle identity for cosine, right? So basically, cosine, remember the identity, cosine 2 theta equals cosine square theta minus sine square theta. This is one of the three variations of the double angle identity for cosine. Alright? So cosine 2 theta is that, so I'm just going to substitute cosine 2 theta with this for this difference of squares right here. So we're going to have y prime equals 5 cosine 2 theta. And that's our final result. Okay? So there you have it. Alright, let's move along to question, this is question 4 I just did. Let's move along to question number 5. For question 5, we're going to be doing y equals sine of 1 minus 5x. Okay? So in this case, you have a linear function inside a trig function. So whenever you have a function embedded in a function, you have to use the chain rule. All right. So in this case, we're going to do find the derivative of ddu of sine u. All right. So ddu of sine u. Okay, what did I just do? I replaced this function, this inner function, with u. So u is basically 1 minus 5x. Alright, so I don't want to get distracted by this. So I'm just replacing with u, alright? when I'm done differentiating this outer function, which is sine, then I'll bother myself with the inner function. So what is the derivative of sine? The derivative of sine is so du of sine u. Derivative of sine is cosine, so this is going to be cosine u. All right. After we differentiate the outer function, then we're going to multiply it by the derivative of the inner function. All right. So let's go ahead and do that right here. So the derivative of sine is cosine, so we're going to have, this is going to become y prime is going to be, the derivative of sine is cosine u, but u is 1 minus 5x, right? So it's going to be 1 minus 5x. That's for the outer function, times, now we have to now differentiate the inner function, which is 1 minus 5x, so 1 minus 5x prime. Alright, so the whole idea of the chain rule is you do the outer function first, blinding yourself to the inner function, so it doesn't change, and then you're going to differentiate the inner product, the inner function, and multiply your initial result with whatever you got. Alright? So now what's the derivative of that? We just simply use the power rule, right? So it's going to be cosine 1 minus 5x. The derivative of 1 is just 0. So it's going to be 0 minus the derivative of 5x. You factor out 5 and differentiate x, you get 1. So it's times 5 times 1. Alright? Okay, so this is basically negative 5. So y prime is going to be negative 5 cosine 1 minus 5x. And there goes your final result. Alright? Excellent. Now let's move along to the next example. Example number 6. What if we had the function y equals 3 secant 3 over the square root of x squared plus 1. Alright, let's go ahead and do this. So we're going to use a chain rule here also because we have a function inside a function, but we have a radical in the denominator. But is there a way I can express this without a denominator? Well, let's see. What if I write this as y equals 3 secant? Using the law of exponents, this becomes 3 over, square root is the same thing as raising the quantity to the 1/2 power, right? Like that. And then I can rewrite this as y equals 3 secant 3 times x squared plus 1 to the negative 1/2. Whenever you reciprocate, you negate the exponent, right? So you see how I rewrote this? Instead of having a square root in the denominator, I just have a numerator here, which is much easier to differentiate, okay? So now, what's the derivative of secant? In this case, I want to blind myself to this function right here. So I'm going to be differentiating the dx of secant u. Okay? In this case, u is basically 3 times x squared plus 1 to the 1/2, actually to the negative 1/2. So let's forget about this and call it u. Alright, so the derivative with respect to x of secant u is going to be secant u tan u times du dx. Okay? So, forgetting about this, if we focus our attention on secant, the derivative of secant is secant and tan. So, y prime is going to be, this is a constant, so we just leave it outside, times secant of u, but remember, u is this interior function right here. So, instead of writing secant u tan u, I'm going to write secant secant of 3 times x squared plus 1 squared, x squared plus 1 to the negative 1/2, tan of the same story, tan of 3 times x squared plus 1 to the negative 1/2, that's secant u tan u. And now using the chain rule, I'm going to differentiate the interior function. So I'm going to be doing times 3 times x squared plus 1 to the negative 1/2 prime. Alright, so this is basically the du dx that's illustrated here in my chain rule. Alright, so let's rewrite this. We're going to have y prime equals, since I'm done differentiating this, I can rewrite this without the negative exponent, so it's going to be 3 secant 3 over the square root of x squared plus 1 times tan of the same story, 3 over the square root of x squared plus 1. And now the derivative of this, we're going to use a chain rule again. In this case, we're going to be computing d dx of u to the negative 1/2. Alright, in this case, u is going to be the inner function here, which is x squared plus 1. So forget about x squared plus 1. Let's focus on this negative 1/2 power. So using the power rule for this, the derivative of u to the negative 1/2 is negative 1/2 u to, and then you bring the power to the front and subtract 1 from the power, which is negative 3 over 2 times du dx. Alright? So if I do that, for here I'm going to have, there was a 3 there before, so it's going to be 3 times negative 1/2 u, but u is x squared plus 1, so let's put that there, x squared plus 1, to the negative 3 over 2, that's what we found here when we subtracted 1 from the power, times the derivative of the inner function, which is x squared plus 1, and I'm going to write that prime. Okay? So one last differentiation, and then that'll be that. Alright, so in this case, we're going to have, this is going to become 3 secant 3 over root x squared plus 1 tan 3 over root x squared plus 1, and then this one is going to be, if you multiply it together, is going to be negative 3 over 2. So negative 3 over 2, we can bring it to the front here. I'm going to multiply them in the next step, negative 3 over 2. This has a negative exponent, so it's going to become 1 over x squared plus 1 raised to the 3 over 2. If you have a negative exponent, you reciprocate it, right? Now the derivative of this is just simply use the power rule for the x squared, which is 2x, and the power rule, the constant rule for 1 is 0. Okay? So if I want to write this whole thing together, note that this 2 and this 2 cancel out right there. So I can write this entire derivative. Let's see, I can write this as follows. Alright, so after the 2's cancel out, it's basically going to be, our result is going to become y prime is going to be, this x can be brought to the front, so we have negative 9x times, that's 3 times 3 times x, secant of 3 over the square root of x squared plus 1, tan 3 over the square root of x squared plus 1, and then we divide the entire story by the denominator, which is x squared plus 1 to the 3 over 2. So divided by x squared plus 1 raised to the 3/2 power. Okay? So this is a little bit long and messy, but there you have the derivative. Because in this case, we're using the quotient rule, and we're using the trigonometric substitution, the derivative of trig functions, and also the chain rule simultaneously. Alright? So there you have it. Alright, so thanks so much for paying attention to this presentation. Please subscribe to my videos for more updates on problems where you can practice more differentiation. If you like this video, you can click like down here. If you had issues with it, feel free to post a comment or send me an email, I'll gladly respond. And for more videos, visit my site at mathgoodserve.com. Thanks again and have a wonderful day.